So we should start. Okay, good afternoon. So we have 3 classes remaining, and then we have 2 more classes, but those are reserved for presentations. So I want to finish the proof of the Moran-Hutchinson formula. That's certainly one of the sort of main pieces of this class. 2 other theorems that I want to study, that I want to discuss is what is called, or what I'm calling, the Hutchinson measure theorem. So it's about what is called stationary measures in the context of iterated function systems. And there's this thing called the Elton ergodic theorem, which is sort of like an ergodic theorem for iterated function systems. And these are both related to iterated function systems and the so-called chaos game that Professor Barnsley in his talk also talked about. If possible, I would like to prove them as well, but now that we have 3 classes remaining, it seems like maybe this is not a feasible thing. At the very least, I want to discuss these theorems and some elements of the proof, of their proof. But certainly I would want to spend some more time on this Moran-Hutchinson formula so that its proof at least is more clear, because ultimately this Moran-Hutchinson formula seems to be more technical, and so I think it would be better to at least understand this. So we had done this upper bound last week, and we had started talking about the lower bound, and I'll remind you all that stuff in a second. But before that, I just wanted to rectify some of the items that I think I messed up last week. First of all, this definition of the Hausdorff dimension. We discussed this. I sort of discussed this, but I think we can sort of think about it or discuss it even more clearly. I want to sort of spend some time on even the definition of the Hausdorff dimension, and then the 2 pieces of technology that we're going to use for the lower bound of the Hausdorff dimension, the mass distribution principle, or one version of it, and the covering lemma. So I thought about these, and I think I'm happy with these statements now, and they're like very rigorous as far as I'm concerned. Any questions before I start? Yes?
So this is regarding final report stuff, not necessarily
yes.
This, but would you say it's wise to expect us to make a meeting with you to discuss?
Yeah, sure. Yeah.
I'm not sure if you're leaving comments or if it's more just
Yeah, I mean, I am reading the first drafts of final reports, which you submitted on Sunday, but it's taken some time. And compared to the weekly reports, for the final report, I'm also going to sort of add more comments about sort of like the aesthetics or the optics of the things, like, because I want you to sort of have some exposure to this more sort of formal way of, more professional way of expressing oneself. So I'm sort of annotating the reports. And ultimately, I would hope that we have a meeting as well. Any other questions about the final report? Okay. Oh, so I guess so this Sunday, the draft for your presentations are also going to be due, I believe. And I will send an email about this as well. But ultimately, I also would want you to send me the title of your talk and an abstract, because ultimately I want to sort of write down a schedule for the presentations and then sort of distribute them so that it's sort of like a simulation of a conference. This is sort of typically what happens. Typically, if you're gonna give a talk at a conference, the organizers typically ahead of time contact you. They ask you if you have any preferences in terms of the time slots and stuff, and then eventually they also ask you for your titles and abstracts and stuff like that. So since this is supposed to be research or introduction to research, I think it would be good to do that. Anyway.
Can I ask one more question?
Yes.
What are you looking for in our not first draft, outline of our presentation? What should we be turning in?
I mean, something that ultimately satiates my worries that Yes, like I want to have a sense that you know what you're doing, and it doesn't need to be 100%, but at least like you have a direction and so on. That's it. Yeah. Any other questions? Okay. So definition of Hausdorff dimension. So recall that we defined this Hausdorff dimension in 2 steps. First, so we have an X metric space, a subset A, and we had these family of outer measures, outer S Hausdorff measures and so on. And so the way we defined it was we had this expression h to the S sub epsilon of A, so it's the infimum of sums, blah, 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 and then we took that epsilon to 0, and that was the S outer measure. And the definition of the Hausdorff dimension really is about how the value of the S outer measure of a specific set varies as you're changing the parameter S. And so we had this inequality. If I have 2 values, S1 and S2, such that S2 is larger than S1, then for any epsilon, I have this inequality. And the definition of the Hausdorff dimension is ultimately based on this inequality. Okay, I'm not going to redo this again because I think that was fine. But what I want to do is I want to give a clearer explanation as to why this number, the sup of all those parameters S, such that the S outer measure is infinity, is equal to the nth of the set of all those parameters S, such that the S outer measure is 0. So that ultimately I want to say that, oh, there is a unique phase transition from outer measure being infinity to outer measure being 0. And that unique phase transition is, by definition, the Hausdorff dimension. Okay? So I have 2 subsets of the reals. So let me call this S sub infinity, and the other one S sub 0. For brevity. So I want to say that S infinity, so the sup of S infinity is equal to the nth of S0. First, let me do this. Let's first verify that any value here in S infinity is bounded from above by any value there. So let S in S infinity, and let me say T in S0. I claim that this happens. Okay? And ultimately, I'm going to use this, right? So S being in S infinity means that the S outer measure of A is infinity. But this S outer measure, maybe I should write it the other way around, is a limit as epsilon goes to 0 of h to the S sub epsilon of A. And since as I'm changing the epsilon, or as I'm making epsilon smaller and smaller, the S to the h to the S sub epsilon increases, I can really think of this as the sup. Maybe I should have done that way around. Okay, doesn't matter. Okay, and likewise, since t is in S0, I have this. Again, this is the same thing as a sup over all epsilons. Of h to the t sub epsilon of A. Well, okay, these are non-negative numbers, and I'm saying that the sup of all of these things is 0, which means that for any epsilon, really, this is 0. Epsilon positive. Well, if for any epsilon, this value is 0, So I'm trying to use this inequality here. Yeah, I can do the following. Say otherwise. I.e., so the negative of this or negation of this is S is strictly larger than T. Okay, that works, I think. If S is strictly larger than T, then plugging these two values into this expression, I have the following. So you see, S2 I'm choosing as S, and S1 I'm choosing as T. S2 is S is bounded by epsilon to the T minus S times H to the T sub epsilon of A. Okay? Okay, now it's all good. Because you see, because of this, right, H to the T sub epsilon of A for any epsilon is 0, which means that this is 0. Epsilon is positive, which means that this is also 0. Well, if for any epsilon, H to the S sub epsilon of A is 0, that means that the limit 2 has this value, which means that H to the S cannot be infinity, a contradiction. Which means that this cannot happen, which means that the claim is true. Any questions about this? So to wrap up, I take an S in S infinity and T in S0, and I want to show that S is bounded from above by T. I'm assuming otherwise. Say the other way around works, but then plugging in these values in the appropriate places in this inequality, I get that because this value is 0, this value too is 0, which means that S cannot be in S infinity, and that's a contradiction. Therefore, this has to happen. Okay, so that's the first step. The second step is that, okay, so once you have this, this really tells you that the sup of this set is not larger than the inf of this set. It doesn't say that they're equal. So we need to have another argument for this. So let me just say dot, dot, dot. Thus, sup of S infinity is bounded from above by the inf of S0. Now I want to say that these are equal. Say they are not equal, which means that sup of S infinity is strictly less than inf of S0. So, equality, say otherwise, i.e., sup of S infinity is strictly less than inf of S0. Okay. So let me draw a picture. So initially we start at infinity, of course. So I'm imagining that the picture is perhaps something like this. I don't know what happens in here, but you see this is the sup of S infinity and this is the inf of S0. And these two sets ultimately I'm assuming that they don't kiss. Okay, if they don't kiss, that means that there is a value in between them. Okay. So let's say, let's abbreviate these things. Let me call sup lambda for left, and this inf rho for right. And let me take their average, for instance. That would be certainly a number between. And let me call that mu for middle. So I'm choosing some point in between. It doesn't really matter what the value of mu is, but it's here. That's my mu. Okay. Now, if I were to choose a value s that is here, it's strictly between lambda and mu, which I can certainly choose because mu is certainly not equal to lambda. It's strictly larger. Let us be a number between these two. Well, S cannot be in S infinity because I'm saying that it's some number that is strictly larger than its sup. S infinity, sorry. What does it mean for a parameter S to be not in S infinity? It means that the S outer measure of A is not infinity. It's a finite number, possibly 0, but it's a finite number. Okay. Now I'm going to, again, use this inequality with S and mu. Mu is larger, which means in this inequality, I'm going to use S2 equals mu. So h to the mu sub epsilon of A is bounded from above by epsilon to the mu minus S times h to the S sub epsilon of A. Well, this S-dimensional outer measure is a sup of all of these. And I'm saying that the sup is finite, which means that for each epsilon, this is a finite value. If for each epsilon, this is a finite value, as I take epsilon to 0, the right-hand side is going to decay to 0, because this goes to 0 no matter what. Okay? This is finite. This converges to a finite value. This converges to 0, which means that the mu outer measure of A has to be 0. Well, if the mu outer measure of A is 0, then by definition mu has to be in S0. But I chose mu to be a number that is strictly less than its infimum. That cannot happen. Which means that this assumption is false. In other words, these two sets, S infinity and S0, have to kiss. There's no gap like this. Okay? And the common value I define as the Hausdorff measure, Hausdorff dimension. Does this make sense? Okay, this is not sophisticated, but it's a fundamental idea. Any questions?
I missed the second half of the whole contradiction here on this Hausdorff new one. Could you explain just the last little bit of that one more time?
From here to there?
Specifically just the contradiction that I read.
Oh, do you agree that the mu Hausdorff outer measure of A is 0? Okay, if that is the case, by definition, mu has to be in S0. Because S0 is this collection of all those parameters for which the outer measure is 0.
Yeah.
But I'm choosing mu to be strictly less than the infimum, which means that this mu cannot be in this set S0.
That makes sense.
Yes. Okay. So you see, it all comes from this. You're just changing the parameters and you're looking at epsilon versions and taking epsilons to 0. Okay, good. That's the first item. Second item, I want to sort of go over these two pieces of technology that we're going to use. First is mass distribution principle. Okay. Basically, these statements are logically equivalent, as far as I'm concerned, to the versions that we sort of figured out last week. But this is sort of really the more psychologically proper way of stating them, it seems like. Because you can take a mathematical statement, and there are infinitely many ways of restating them using sort of logical tautologies. But sometimes, given a certain situation, one statement works better than some other statement. So you can turn it to contrapositive and stuff if you want. So the statement for the mass distribution principle that I ended up liking the most is the following. Let X be a metric space, S be a parameter, and A be a subset. I want to bound from below, ultimately, the Hausdorff dimension of A by S. So the mass distribution principle is all about this. I want some stuff so that ultimately the Hausdorff dimension of A is bounded from below by S. The statement is the following. If there's an outer measure mu star on X, such that the following two things happen. Namely, that if there's a gamma and epsilon star such that for any subset B of diameter bounded from above by epsilon star, you have this inequality. So the outer measure relative to mu star is bounded by gamma times diameter to the S, which means that for small subsets of X, you have sort of a relationship between diameter to the S power and mu star. Okay? So you're sort of relating size coming from mu star and diameter to the S. And if A happens to have positive measure or outer measure relative to mu star, then the S dimensional or S Hausdorff outer measure of A is positive, and consequently the dimension, Hausdorff dimension of A is bounded from below by S. That's a statement that I think works the best. Any questions about this? Okay. Okay, let me go over the covering lemma that I liked the statement of as well, and then we can perhaps think a little bit more. And so the covering lemma goes like this. Let X be a metric space again, and curly U be a collection of pairwise disjoint open subsets. Could be infinitely many, whatever. It could be finite too. All I care about is that the two cells in curly U don't intersect. And I have four parameters, R, lambda, rho, alpha. These are all positive numbers. If the following two assumptions are satisfied, namely that for any cell U in curly U, there are 2 points x sub u and y sub u, such that the open ball centered at x sub u of radius lambda times r is included in U, and in turn, U is included in the open ball centered at y sub u of radius rho times r. And there's a measure, mu, such that relative to this measure, the size of any ball of radius r grows like r to the alpha up to a constant. Then for any z, any point in X, the number of cells in my collection whose closures intersect with the open ball centered at z of radius r is non-empty, is bounded by this number, 1 plus 2 rho divided by lambda to the power alpha. Okay, so this really tells you that if you have these assumptions, which kind of look bizarre, but in the proof, you're going to see how this is sort of like a natural thing. These two assumptions are natural things, in a sense, at least in the context of the Moran-Hutchinson formula. It says that if you have a bunch of open sets that satisfy these nice properties, then if I were to take a small ball of radius r, at most I'm hitting this many of those open subsets. Okay? So the intersections are sort of controlled in a sense. Any questions about the statements of these two? Should I redo the proof of this statement?
I hope okay by the end of class with it.
Okay. Okay. What do you think? We can just take it as a black box as well, but you know, the proof that I wrote ultimately I think made sense. Basically, using this, so what you do is the following. You start with, you sort of open this definition up, and you cover A by counting the many subsets of small radius, and then using this property, you bound the outer measure from above by the h to the s sub epsilon of A, and then you take the limit and so on. That's sort of like ultimately the proof of this. But we didn't finish the proof of this, so maybe I should spend more time on this. Okay. So, okay, I'm skipping the proof of mass distribution principle. I'm just going to try to prove the covering lemma. I should also mention that really these two pieces are somewhat related, you see. In the mass distribution principle, you have this. And in the covering lemma, you have this relationship. So ultimately, you want to sort of tether the notion of size, in other words, the measure or outer measure, whatever you have, to the notion of the geometric notion of diameter. And so this really is a statement about sort of the density of the measure. And this too is about the density. We're not going to discuss densities or dimensions of measures themselves, but one can and does talk about these kind of things as well. Not only can you talk about dimensions of subsets, you can talk about dimensions of measures. And in a sense, that's perhaps more reasonable, in fact. Okay. So I want to start with the following. Let me take, so you see, R, lambda, rho, and alpha are fixed, and I have these two properties already. I'm assuming these. Let me take a Z, and let me look at an open ball, centered at Z, that intersects with some cell U, or rather the closure of such a thing. Such that the open ball centered at Z of radius R hits the closure of U. Okay? So this is non-empty because I'm going to take a point in this. Let's take a point Y. Non-empty. Now, what I want to say is something like this. U is in fact included in, or rather the closure of U is included in a ball, in a certain ball, centered at this Z. Okay? So maybe I should draw a picture. Let's say this is my U. By assumption, there's an X sub U such that, maybe here, the lambda R ball in X, centered at X sub U is included completely inside U. And in turn, U is included in some larger ball. Maybe I want to have this one. I'm not talking about anything about optimality. Let's say this is Y sub U, and this radius is rho times R, and the radius over there is lambda times R. Okay? And so now I'm saying I have another ball centered at another point of radius R. So let's use red. That intersects U, or rather the closure. But of course, drawing the closure of a subset is not easy, so I'm not going to draw it. But let's say that my ball is like this. So z is here, of radius r, and there's an intersection, as you see. I want to say this. By enlarging the radius here, so in this picture, for instance, if I were to look at this ball, certainly I can include u inside this larger orange ball. Okay? I want to figure out what that radius is. Well, this is this part I did last time too, but I just wanted to go over it. So if I were to take a point in u, let's say no, let's just say u. I'm going to look at the distance between z and u. I'm going to look at this. I'm trying to bound that, basically. Well, injecting this middle point, I had the following. So, okay. Now, by definition, y is inside the r ball centered at z, which means that this distance is bounded by r. How about this? Well, both y and u are in u bar, the closure of u. Well, that means that this value is bounded by the diameter of u bar. But then, I had assumed that u is included in this open ball, which means that its closure is included in the closure of this ball, which itself is included in the closed ball with the same values. In other words, this diameter is bounded by 2 times this. So this is strictly less than r plus 2 rho r, which is equal to 1 plus 2 rho times r. Okay? So this 1 plus 2 rho in the numerator in the upper bound here does come from that. That's that part. Any questions about this so far? Okay. Well, in other words, you see, ultimately, so this says that u is included in, well, I can use a closed ball too if I want. It's included in the closed ball centered at z of radius this. But this is true for any cell u that hits this ball. Okay? So I could take the union of all such u's if I wanted, and this ball would include all of them. Okay, well, let me just delete this picture now, because I need some more space. Now let's look at this. So let u1, u2 dot 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 uq. I'm taking finitely many cells in u such that each of them hits this guy. Such that for any I, the closure of u sub I hits the open ball centered at z of radius r. What is the measure of their union relative to mu? This measure that I assumed I have. 1 to q, like this. Well, because each u sub I has closure that intersects with this ball, that means that this union really is a subset of this subset. Which means that the measure of the union is bounded from above by the measure of this set. But by assumption, the measure of that subset is gamma times radius to the power alpha. Okay? So the radius is 1 plus 2 rho times r to the power alpha. But then ui's are disjoint, which means that I can take this union out, and it would be the same expression. Okay, each ui includes some ball of radius lambda times r by assumption, which means that, let me just write it like this. If I were to replace ui by those smaller balls, the measure would possibly decrease, but it would not increase. Oh, sorry, this is q. That's q, and this is mu of x sub I, let's say, lambda r. Because each such ball is inside one of these, which means that the sum of their measures is going to be bounded from above by the sum of the measures of ui's. Well, again, by the assumption on the measure, I know that the size of each of these is, well, gamma times lambda r to the alpha. But I have q of them, which means that this value is exactly q times gamma times lambda r to the power alpha. So ultimately we have the following. Q, the number of balls I could choose that intersects this ball. Q times gamma times lambda r to the alpha is bounded from above by gamma times 1 plus 2 rho times r to the power alpha. Canceling things out, so the gammas cancel and then r's cancel. I have that Q is bounded from above by 1 plus 2 rho to the alpha divided by lambda to the alpha, which is the bound that I had assumed, I had claimed. Questions? It's really not that sophisticated. You're just counting. You're just using volumes and measures and stuff. Okay. So these well, we covered. Let's now get back to the proof of the lower bound. Now, the Moran-Hutchinson formula is really for a very specific case of a BIFS, but still the ideas, as far as I understand, they are rather universal. So we're going to have some interesting ideas in the proof, and they're sort of like typically what people try to use when they're trying to sort of compute the dimension of something. Okay, so let me remind you the setup. Dimension formula. As usual, I have a BIFS. Finitely many contractions acting on some complete metric space. I'm assuming because the other way around it's rather trivial, I'm assuming that each of these contractions, or rather none of them, is a constant function. And the notation that we were using was the following. Oh, let me just use these actually first. So we have the unique attractor A sub W, and we have the coding map, Hutchinson coding map, coming from the shift space with n symbols onto the attractor, coding map. Let me let capital L sub I to be the Lipschitz constant of Wi. Of course, each of these is a contraction, which means that this number is less than 1. And then I have two more values. Lowercase l, I'm going to define as the minimum of these. So let me write it like this. It's a positive number because I'm assuming that none of these is a constant. And further, I'm going to assume that they're all similitudes, but we'll see. And then the max of all of these Lipschitz constants, let me call capital L, which is a number strictly less than 1. OK. I have three assumptions. First, that X is a Euclidean space. So X equals RD. Second, each Wi is not only a contraction, but in fact, it's a similitude. OK, and then the third, of course, is that this iterated function system satisfies the open set condition. And let me also let S to be the upper similarity dimension. The unique number such that L sub I to the S, when added together, gives me 1. Okay. We had already showed that the S outer measure, or outer S Hausdorff measure, or whichever combination you want to say that, of the attractor is bounded from above by S. Sorry, it is finite, which means that the Hausdorff dimension is bounded from above by S. That's shown. We had shown that the outer S Hausdorff measure of A sub W is bounded from above by infinity, which means that the dimension is at most S. So next, we want a lower bound. We want a lower bound on this guy. We want a bound from below the Hausdorff dimension of the attractor by S. And the way we're going to do this is by verifying that the outer S Hausdorff measure of A sub W, and even though I keep saying outer, because A sub W is a compact subset, it's in particular closed, which means that its complement is open, which means that it is in the Borel sigma algebra. Since any Borel subset is measurable relative to any Hausdorff measure, I don't need to say outer measure, really. This is really the Hausdorff measure. I can say it. But never mind. Keep missing it. In any event, I want to show that this value, Hausdorff measure of dimension S of A sub W, is a positive number, which consequently will tell me that the dimension, Hausdorff dimension, of A sub W is bounded from below by S, which together with this gives me that the dimension is equal to S. So this is what I want. Questions about this? Okay, so we're going to use the mass distribution principle. So for the mass distribution principle, we need an outer measure, but really we're going to define a certain dynamically relevant actual probability measure. Now, let's look at this. This says that really the tuple whose entries are each of these numbers is a probability vector. So let me define P to be L sub 1 to the power S, L sub 2 to the power S, and so on. In other words, this is a vector in the n-1 dimensional standard simplex. Now, using these values, what I want to do is I want to define a probability measure really on the shift space. Okay? I'm going to define a probability measure that is really invariant under the shift transformation. Then what I'm going to do is I'm going to push it forward. We're going to discuss what that means in a second, using the Hutchinson coding map. That probability, that's going to give me a probability measure, and it's going to be supported, I'm going to define it as well, on the attractor. Okay? So, this defines a unique probability measure, Borel probability measure. I'm just going to leave it as this, probability measure. That I'm going to denote by mu sub p. Recall that this was our notation for the collection of probability measures on a metric space. Pushing mu sub p forward via the Hutchinson coding map phi sub w gives a unique probability measure on A sub w. Gives a unique probability measure I'm going to denote this probability measure as by nu sub w comma p. It depends on both the iterated function system and the probability vector that you chose. And so this is one of the notations for the push-forward operation. I'm just going to write it like this. In a second, I'm going to discuss, after our break, I'm going to discuss all of these, at least to some extent. And next week, or maybe on Thursday, when we start talking about Hutchinson measure theorem, or the Elton ergodic theorem, it's really about measures that are defined this way. It's going to turn out that this is the unique stationary measure relative to this mu sub p and so on. So ultimately what we're going to do, once we're done with the proof of the Moran-Hutchinson formula, is that we're going to define a certain contraction called the Markov operator associated to an iterated function system acting on the space of probabilities. Because it's a contraction, we're going to discuss at least a little bit that this space, however you do this, is a complete metric space because it's this Markov operator is a contraction. It is a unique fixed point. It turns out that this is the unique fixed point. That's what we're going to do after we're done with the proof of this. But for now, I have this measure. And what I'm going to do is I'm going to use this measure as this outer measure in the statement of the mass distribution principle. So we'll use mu sub w comma p as mu star in mass distribution principle. Because you see, I'm going to discuss this in a second after the break, that this gives probability or measure 1 to the attractor. So it satisfies the second property in the mass distribution principle. We're going to have to argue a little bit to bound the measure relative to this with the diameter to the power s up to some constant. And so that's going to be somewhat interesting and the more technical part of the proof. But once we have that, we're going to have the dimension estimates that we want. Okay, so this is where we're going so far. Let's take a break, and then when we get back, we're going to continue. Are we all back? I think so. Okay. Okay, so before going further, I want to give at least some definitions as to why these things are. But these are these operations defining this measure on the shift space and using this push-forward operation is rather common techniques in modern-day dynamics. I just want to mention them a little bit. Before going into that, I forgot to give this exercise. This is a nice exercise that sort of relates Hausdorff dimension and the Minkowski dimension, really. The exercise is the following. You can define the Hausdorff dimension of A as the infimum of all those parameters S, such that what is called the unlimited S Hausdorff content of A is 0. So you see, we had this h to the s sub epsilon of A, and we said as epsilon is decreasing, this value is increasing. And by taking epsilon to 0, we were able to define this outer measure. Well, instead of taking epsilon to 0, you can take it to infinity. That still gives you a value that is significant. And that is what is called the unlimited S Hausdorff content. So you can define the dimension like this as well. And it turns out, we're not going to spend time on this, but you can define the lower and upper Minkowski dimensions in a similar sense, in a similar way. You have sort of something like this that sort of interpolates ultimately Hausdorff dimension and this Minkowski type dimensions. Okay, so first let's talk about how this probability vector defines a probability measure on shift space. Now last week we talked about how a probability vector like this defines a probability measure on a finite set. So recall that we can think of this set as a measurable space where any subset I'm declaring to be measurable. And the probability, maybe let's call it probability measure C sub p. C sub p of the singleton I is nothing but p sub I. Right? That's the probability measure. But when you think about it, you want to sort of relate these values, the entries of this probability vector, p1 to pn for brevity, to something that is really, it's like you want to relate it to a sort of experimental something. So, for instance, if I were to take n equals 2, this was the example that I gave. Of course, p would be of the form a and 1 minus a. Or maybe I should write it like this. P sub heads, and then 1 minus p sub heads, and that's supposed to be p sub tails. So p sub heads, right, the first entry of the probability vector, represents the probability of, in a coin flip, heads being the outcome, and 1 minus that number represents the probability that tails comes as the outcome. But when you think about it, what does it even mean when all you're doing is only one coin flip? Really, you're making sense of probabilities when you have a large amount of experiments. And from a probabilistic point of view, this shift space really is representing that. So this finite set represents just one coin flip. It's almost meaningless to talk about the probability of that. Right? Because if this is your world and all you do is one coin flip, it's like, it's not very easy to talk about the probabilities. This represents one coin flip. But shift space with two symbols represents infinitely many coin flips. And the way you would really think about perhaps this probability vector, if at all, is by saying that, oh, I'm just going to tally up the number of heads against the number of tails. Right? Really, the probability of heads for this specific coin flip, insofar as two different coin flips are what are called independent, and they are distributed according to the same probability distribution. Again, I'm not going to go too much into details about this. This probability of the outcome being heads, should be the average of the number of heads in sort of like a large sample. So 1 over n, and then number of heads in the first n flips for large n. Okay? The larger you take n, the closer you should get to this probability, and in the limit you should be equal. This is, if you're a probabilist, you call this a strong law of large numbers. If you're a dynamicist, you just call this an ergodic theorem. So let me write this. So, strong law of large numbers, or ergodic theorem. And this Elton ergodic theorem is sort of a version of this. It's not very sort of bizarre of a thing. And so based on this, how do I define this mu sub p on the shift space? Well, I'm going to use what are called cylinder sets. Any questions about this heuristic before? Okay. Okay, so if this is the case, maybe I should ask this. So I have, again, the coin flip, and I'm looking at the shift space. In other words, I'm imagining infinitely many coin flips, and I have this fixed probability. At each experiment, at each coin flip, my model is so that the probabilities are always the same. And the probabilities are independent. So the probability of heads coming at the 55th coin flip has nothing to do with the probability of heads coming at the 75th coin flip. If that is the case, what should be the probability of two heads? Let's say that the first coin flip is heads, the second coin flip is heads also. What is the probability of this?
Square of the probability.
Right, so the probability of this times the probability of this. And if this were a tails, you would say P sub h times P sub t. The way you did, so you sort of like soup this up, and that gives you this probability measure, okay? And so here's some formalism. Let Z be a finite subset and let me let beta to be a function from Z to the alphabet. Then the cylinder set determined by these two is the following. Then the associated cylinder set of shift space is C of Z comma beta. Now this is just going to be the collection of all those sequences such that for the corresponding indices, corresponding times, the entries should match up with the beta. So omega in shift space such that for any I in Z, omega sub I equals beta sub I. Okay? It's a certain nice subset. In fact, this is a closed subset. Let me introduce some more notation. If Z is the first, let's say, lowercase n entries, then I'm just going to use beta. If Z is like this, or if beta is perhaps a periodic point, this is just notation that I'm going to use. C sub beta equals okay, I'm just abbreviating this. So here is sort of like a more explicit way of thinking about this. I'm just going to erase this exercise. So for instance, consider the following. So it's very important to get comfortable with these cylinder sets, because when you're trying to talk about something more quantitatively, these are sort of like the nicest sets that you can use in the context of shift spaces. And so the notation really is very useful. So say n is 2. Okay. And let me let Z to be 0, 1, 2, 3, 4. First 5 entries. And I'm going to define beta to be this function. So it goes from here to 1, 2, capital N. So all I need to do is to list, right? So 0, let's write it like this. I'm going to write it as a tuple. Let's say it is 1, 1, 2, 1, 2. Okay, so this means that beta 0 is 1, beta 1 is 1, beta 2 is 2, beta 3 is 1, beta 4 is 2. Now the cylinder set, defined by this, is the collection of all those sequences in shift space whose first 5 entries are like this. Okay? Okay, I'm not going to write this again, but another way of denoting this that I like is by using ticker tapes. And so what I'm going to do is the following. I'm going to put the entries, the specific entries that are given to me, and the other spots, I'm just going to put a star representing a wildcard. Okay. So in our notation, this is the 0th entry, 1, 2, 3, 4, 5, and then maybe 6. So this is 1, 2, 1, 1, 2, 1, 1, 1, 2, 1, 2. This one, it's a wildcard. In the cylinder set, it is not determined whatsoever. This too is a wildcard, and so on. Okay, this is another way of thinking about this. Any questions about this definition of the cylinder set? Okay. And so the reason why I'm defining the cylinder set, apart from it being useful, is also it helps one to define this mu sub p. Well, based on our heuristic, what I should say is something like this. The size of the cylinder set relative to mu sub p should be the product of the corresponding probabilities of these symbols. So I need to tell you what the size of this is relative to mu sub p. Well, I just need to multiply the corresponding entries for coming from p, right? So this is just going to be product of all i's over z, p sub beta sub I. Whatever you said earlier about the heads and tails and their probabilities is formalized by this idea. Okay, now I'm not going to prove that this indeed defines a probability measure, because after all, I need to say something about what is the size of any Borel measurable subset. I'm just defining mu sub p on these very nice subsets. But it turns out there's a technology that guarantees this, coming from stochastic processes, basically. Because ultimately, this is sort of modeling independent and identically distributed discrete time stochastic process. And so I'm just going to leave it as an exercise for you to read about this. This defines a unique probability measure on shift space. And basically the name of this technology that allows you to do this exercise is what is called the Daniell-Kolmogorov consistency theorem. This really is a specific case of this theorem. if you look at any ergodic theory book, you wouldn't be able to find the proof of this typically, but at least you would find references. Okay, so we have a measure. In fact, this measure is shift invariant, so that's not going to be useful for the purposes of the Moran-Hutchinson formula, but it is an important thing. Right, from a heuristic point of view, getting two heads consecutively, it actually doesn't matter insofar as the events, the outcomes, or rather the experiments are independent. It doesn't matter where you're trying to see. Like getting two heads starting at time 0 has the same probability as getting two heads at time 55,000. That's sort of like the formal way of saying this, or that's the heuristic way of saying that it is shift invariant. I recall that this means that for any Borel measurable subset, the measure of B is the same thing as the measure of its pre-image under shift. Okay. So if I were to take a subset, shift it this way, the probability is going to be the same. The likelihood of an event happening doesn't change in time. Questions? And now we have a couple minutes left. And really here, we're also seeing this notion of a push forward. Instead of writing, maybe I should be more clear here. Let me write it like this. In this expression, instead of saying, oh, this is the mu sub p measure of the pre-image of B under shift, I'm going to say this is the measure of B under some other measure, and that's going to be the push forward. So instead of writing it like this, I'm going to write it like this. Shift sub star of mu sub p of B. And that is the push forward operation. Okay? And so let me define that formally as well. Let's say f xb to yc be a measurable function, be measurable. This means that any set in the sigma algebra has pre-image in the sigma algebra. And for any mu, let's say probability measure on the domain, its push forward is a probability measure here defined by, well, the measure relative to the push forward is the measure of the pre-image. Okay? So we have a shift, we have a probability measure on the shift space. Using the coding map, we can push it forward to get a probability measure on the attractor. Now that probability measure is dynamically significant, ultimately because of the fact that this measure that we started with was shift invariant. And we're going to use that to lower bound the Hausdorff dimension, Hausdorff measure. Okay, thank you. I'll see you on Thursday. Okay, let's start. Good afternoon. So today I'd like to finish the proof of the Moran-Hutchinson formula, the lower bound. We have pretty much everything we need to go through the proof. So let me remind you some basics. some notation. We have, as usual, a BIFS, finite many contractions acting on a complete metric space X. I'm denoting the Lipschitz constant of the ith transformation by capital L sub I. Phi sub W is the Hutchinson coding map coming from the shift space onto the attractor, the compact non-empty subset of X that is invariant under my iterated function system. And some more notation. Lowercase l is going to be the minimum of the Lipschitz constants. So it's the maximum amount of contraction that you can observe among all the transformations. And capital L is the maximum of the Lipschitz constants, which is the worst amount of contractions you can observe. S, lowercase s, is the upper similarity dimension, which is the unique number s such that this holds. Recall that what we did last time was we took all of these summands and put them in a vector. And so that's giving me a probability vector in the n-1 dimensional standard simplex. And we talked about how choosing a probability vector like this defines a unique probability measure, mu sub p, on shift space. And I gave it as an exercise that this probability measure is also shift invariant. And then what we did was we talked about this push-forward construction or operation. So now that you have a probability measure here, and now that you have a continuous map, which is in particular a measurable map from the shift space to this, what you can do is you can take the measure here and push it forward using this. And so that I denoted by nu sub w comma p. And so that's a probability measure on the attractor. Now, some more terminology, because now that we're talking about the measures, I think it will be a missed opportunity if I didn't give these definitions. So if I have a more general situation, if I have a measurable space, xb, and a measurable transformation from it to itself, so I have a dynamical system, I'm going to call and I take a probability measure mu that is invariant under F. So this is my notation for the collection of all F invariant probability measures. I'm going to call the pair mu comma F ergodic if the following happens. What does this say? This says that any invariant set is either negligible or its complement is negligible, which means that if you have an invariant set, basically it has to be everything, unless B itself is nothing. So this is sort of like a formalization of the idea that if this is your ambient space and X is acting on it, if you have an invariant subset, this is sort of like B, this must be negligible unless it is everything to begin with, up to a measure zero subset, of course. But the idea here is that this F transformation sort of like mixes every single part of the ambient space. And so here's an exercise. Oh, let me also mention this. Typically, people would sort of like fix a transformation and then an invariant measure, or they would start with a measure and then find an invariant, find a transformation that preserves that measure and so on. And they would say either the measure is ergodic or the transformation is ergodic. But really nowadays, people are thinking of these as sort of like pairs. So you have a dynamical system together with a sort of like a way to measure things. So this is, you should think of this as a pair. And an exercise is that this is ergodic if and only if you have this basic asymptotic independence property. So we didn't talk about this much, but so far when we were discussing measures and stuff, we only looked at the so-called additive structure. We said, oh, if you have two subsets that are disjoint from each other, the measure of their union should be the sum of their measure. Now, the second thing you want to look at is the intersection. What is the measure of the intersection? Basically, independence says that if you were to look at the measure of the intersection of two sets that are measurable and all that stuff, this intersection, the measure of the intersection is the product of the measures. the reason why people typically call this independence, or why this is related to independence, is that if you, for instance, take this mu of b to the other side as a denominator, this left-hand side gives you what is called the conditional probability. So another way of writing this would be mu of a given b equals mu of a. So from a probabilistic point of view, the right-hand side here says that, oh, this is the probability of the event A happening. And the left-hand side says, this is the probability of A happening given that I know that B has happened. So this is you conditioning the probability onto B. And so you see this is sort of capturing the notion of independence, because this equation says that even if I knew that B has happened, the probability of A happening doesn't change at all. Okay. Now in dynamical systems, what you want to say is something like this. You adapt this to a more dynamical situation. You want to say that basically if I were to start with, let's say, a set, and I start iterating it, and then I look at the intersection of this iterate with B. This should remind you of the hitting times in the context of sort of these properties, but in the case of topological category, right? Like we talked about topological transitivity, topological weak mixing, and strong mixing. They're sort of like equal, or they're not equivalent, but they are analogs of these properties. So you want to say something like the size of this hitting for n sometime should be basically this. Again, if I wanted, I could have taken this b to the other side and written this in terms of conditional probabilities, but typically this is what people think. And so, of course, you want this to happen for large n, so, which means that if I were to start with two sets and start iterating one of the sets using my dynamics for large time, basically there should be no correlations left between these two sets. And so the way to sort of like formalize this idea is to take n to infinity and let this, or want this measure to converge to this. It turns out that that property corresponds to what is called strong mixing. If so ultimately, you want this value to converge to the product measure, or products of the measures. If it doesn't happen, this is sort of like a general real analysis principle. If you have a sequence of numbers, and if you have a target value, you can of course ask whether or not that sequence converges to that value. Or if it doesn't converge, then you can ask, does it converge in a weaker sense? For instance, on average, does it converge, and so on. And so that weakening of the senses of convergence gives you these two notions, weak mixing and ergodicity. And so weak mixing would be this, but on average. So one over n k from 0 to n minus 1 mu of f to the minus k of a inter b minus mu of a mu of b equals 0.
So is ergodicity weak mixing the same thing?
No.
Or how do these differ?
With ergodicity, the absolute value is on the outside. So, because you see, if I were to take the absolute value inside, this becomes a larger value. Now, this might converge, but this may fail converging, but not the other way around. Exactly, yes. So, one exercise is strong mixing implies weak mixing, which implies ergodicity. Another exercise is that for any probability vector, mu sub p, this product measure or the Bernoulli measure that we constructed, is strongly mixing, which means that relative to shift transformation, which means that it is weak mixing, which means that it is ergodic. there are many other invariant measures. For instance, well, sigma is shift transformation is a dynamical system. I can look at a measure that is supported on some periodic point, some fixed point, whatever. I can look at some more complicated constructions like Markov processes and stuff. So here, whenever you look at this mu sub p, recall, this represents independent and identically distributed random variables. So the stochastic process is sort of like the most random in a sense. But there are still random, but not as random formalisms that are also very useful. But somehow it seems those are like even more complicated than these to state. So two important properties are what are called K property, that is even stronger than this. And then even stronger than the K property is Bernoulli property, which in fact mu sub p has Bernoulli property. There's also very weakly Bernoulli property, but it turns out that it is equal to Bernoulli property. But somehow it is easier to verify. But anyway, and then there are a couple different sort of generalizations or amplifications of these ideas. Maybe you want to look at not only one hitting time, but multiple hitting times. Or maybe you want to look at not only that these limits are zero, but in fact, you want to figure out the convergence rates and stuff like that. So there's a bunch of work around all this stuff even today. So it's a very active area. Okay. Any questions about these? I just wanted to mention these definitions at the very least. Okay. So let's continue with the proof of the Moran-Hutchinson formula. And of course, these properties are invariant under measurable or measure-preserving conjugacies. I'm not going to define that, but I hope you can guess how that should be defined. Okay. So we had three assumptions on top of all this, namely that first, X is a Euclidean space. Let me write those down too, actually. This is done. X is some Euclidean space. Second assumption, each W sub I is a similitude. In particular, it's a homeomorphism. And third, the iterated function system satisfies the open set condition. Okay, proof of, so what were we trying to prove? We were trying to prove the simple statement that the outer S measure of the attractor is a positive number. That's what I want. And last time I told you that we're going to use the mass distribution principle, and we had this outer measure to use that, and we wanted sort of like some relationship between that outer measure and the diameter to the power s of arbitrary subsets that are sufficiently small. And I told you that the outer measure in the statement of the mass distribution principle was going to be this push-forward measure. Okay. So, by hypothesis, my iterated function system satisfies the open set condition. That means that there's a non-empty open subset U, let's call it, of X. Such that the following two happens. First of all, the image of U under any one of these transformations in my iterated function system is a subset. That is to say, U is forward subinvariant under any transformation. And if I were to look at distinct indices, of course, the images are going to be disjoint. This is literally the definition of the open set condition. So I can assume that U is bounded, because if it weren't, I could have just taken a point in U. And so if this is my U, I can take a point, let's call it lowercase u, because uppercase U is open. There is some R such that the open ball centered at U of radius R is completely inside. And certainly open balls are bounded. Okay, so I can assume that U itself is bounded. If not, I can just replace it with a smaller open ball. Certainly the open ball, that open ball too would satisfy these properties. So without loss of generality, can assume U is bounded. If U is bounded, so is its closure. Is bounded. Well, U bar is by definition also closed. So I have a closed and bounded subset of some Euclidean space. Recall from week 2 or something that any closed and bounded subset of any Euclidean space is compact, which means that U bar is compact. And because U is not empty, so is U bar, which means that U bar is an element of the hyperspace. Okay? Now, I will leave it as an exercise that because of this property, U bar is forward subinvariant under the Hutchinson operator. Okay, which means that Hutchinson to the power 2 is a subset of this, and so on. Which means that if I keep iterating U bar using the Hutchinson operator, I'm going to have a nested sequence of compact non-empty subsets. I think that was an exercise that I gave a while ago, but it is believable. Whenever you have something like this, the Pompeo-Hausdorff limit is in fact the intersection. Okay, and we know that no matter which set you start with, the limit is always going to be the attractor by the Banach contraction principle or whatever, which means that we have the attractor equals the intersection of Hutchinson applied n times to U bar and I have this filtration of sets if you want. Any questions about this so far? So I can take that open set U, which some people call the Moran open set, because Moran was the first guy who realized that, oh, this open set condition is really is useful. I can take it, iterate its closure under the Hutchinson operator, and eventually I'm going to get, in infinite time of course, possibly, I'm going to get the attractor. Now, this also says that for any omega in shift space and for any n, I have the following. You see, because A sub w is a subset of u bar. So because of that, I have this. Recall that this lowercase phi sub w was the cocycle associated to the iterative function system. And by definition, it was the following. You look at this sequence, omega, and you look at the first n terms. And what you do is you compose the corresponding transformations in the corresponding order. So maybe I should remind you. Okay. Okay. Any questions so far?
I'm still a bit confused about how A sub W is the intersection here of the nth iterate of the Hutchinson operator applied on the U bar.
Yeah, because this is the limit of Hutchinson. So this is the Pompeius-Hausdorff.
Does this come from that theorem that didn't necessarily matter where you started?
Exactly.
Okay.
Yes.
That makes sense.
Yes. Any other questions? Now, yeah, ultimately it's not going to matter which open set U that we chose, even though somewhere in the proof we're going to use this specific U. Recall that in the covering lemma we had two numbers, lambda and rho. Those lambdas and rhos are going to come from U ultimately. But we're going to get there. Any other questions? So here's the interesting part. So this is a general idea, which I think people call the notion of a stopping time or defining something using a stopping time. Okay. So this is sort of like the following idea. If you have sort of like a dynamical system or any other sort of procedure that has some time, you have a condition and you define a set or some other object based on how long it takes for a certain condition to happen. Okay? You say, okay, iterate until whatever happens, this condition happens. And then you take the sort of the times where the condition that you want satisfies, and you put them in something. Okay? It's that idea. So let me be more specific. I'm going to choose an R that is a number between 0 and 1. Let me also take an omega. Now I'm going to look at the Lipschitz constants of each of these functions in the cocycle. So omega is fixed, but I'm varying n. Okay? So consider and I'm going to denote it by, how should I denote this? Alpha, beta, gamma, delta, epsilon, phi. Oh, use phi. I'm just going to use r sub n. R sub n, let me let that to be Lipschitz constant of the cocycle at time n. Now this is a sequence of numbers that are between 0 and 1, okay? And furthermore, so I guess when n equals 0, it is 1. So I should maybe write it like this. And furthermore, it is strictly decreasing, right? Because at each step, once I fix my omega, at each step, I'm going to compose yet another contraction. So this has a strictly decrease. Decreasing sequence. I'm going to choose n, which is going to depend on my two inputs, r and omega, such that n is the first time r sub n is less than r. There's a unique integer n that I'm going to write as n of r comma omega such that, well, I can write it like this, right? So at time n minus 1, I'm still above r, but at time n, I'm here. Okay? So this is the Lipschitz constant of phi omega comma n minus 1, and this is the Lipschitz constant of phi of omega at time n. Okay? Now, if I have this, maybe I should draw a picture as well. Oh, let's do this. So recall the cocycle property. It said something about being able to sort of split the integers here as sums. So I can write it like this. Because I'm trying to relate this Lipschitz constant to this Lipschitz constant. So I'm going to try to sort of peel plus 1 from this to get this thing. So I can write it like this. n minus 1 plus 1. Okay. Now applying the cocycle property, this gives me the following. Compose with phi. So sigma, I need to apply sigma once. And then, yeah, it doesn't matter. I can do it this way as well. But maybe I want to do it the other way around, actually. Let me do it the other way around. It's not going to matter ultimately in which order I write, but one way of writing it generalizes, I think, the argument to something else. Let me see. Oh, okay. I wrote the cocycle property wrong. Okay. Exactly. Okay. So the cocycle property says that if this is the first number, you need to iterate this much. Okay, that's what I wanted. Okay. Now, if this is the case, taking the Lipschitz constants, you see, I have that this is the Lipschitz constant of this. which is the Lipschitz constant of the product, which is the product of the Lipschitz constants, by the assumption that these are similitudes. In general, this is subadditive. For an arbitrary iterated function system, if I were to try to split this Lipschitz, the Lipschitz constant of the composition, it would be bounded from above. But in this case, I have this. Oh, it's equal. Times lip of this. And this is nothing but the Lipschitz constant of the n minus first entry of omega 0. This is nothing but L sub omega n minus 1. Now, in general, if you didn't have the similitude property, instead of using this upper Lipschitz constant, which looks at the maximum, you would look at sort of like the minimum. It's like the Lipschitz conorm, if you want. We didn't talk about that, and we're not going to need it, so I'm not going to discuss it. But at the very least, we have this, which means this, that you see, to get from this number to this number, you're multiplying it by this particular guy, which is bounded by lowercase l. Okay, because lowercase l was the minimum of all of these. Well, that means that this is also bounded from below by r times lowercase l. Okay. So maybe I should draw a picture. That's 1. That's 0. Let's say here is r. Let's say here is r sub n minus 1. And I'm saying r sub n is over here. But to go from here to there, you see the ratio between these two numbers is bounded by lowercase l, which means that if I were to look at r times l, it's going to be somewhere here. So I have a very good control over this Lipschitz constant. How much control I have? Well, it depends on how large lowercase l is, really. And so this is also related to this idea of what is called the condition number, for instance, in the context of inverting matrices and stuff. So, so somehow the ratio between capital L and lowercase l, so you want this ratio to be as small as possible. If you can, you want this ratio to be 1, in which case that would mean that each of the contractions are contracting by the exact amount. Okay. It turns out that, for instance, in the context of linear algebra, if you have a matrix that you know is invertible, let's say its determinant is not 0, but maybe some of the eigenvalues are very close to 0, in which case inverting it is not that easy. You end up sort of contributing errors, and the fact that there's this computational difficulty has sort of like a corresponding idea in pure math as well. Anyway, so we have this. So now what I'm going to do is the following. For each r and omega, I have this number, integer, n of r comma omega. I'm going to take omega and chop it off based on this number, and that's going to give me a periodic point. And I'm going to denote it like this. Omega sub r. Okay. Imagine you sort of have like some footage, and then you sort of cut a certain piece of it, and you loop it to upload on TikTok or something. It's that. And so this is going to be it's going to be a fixed point on there this time. Fix of sigma to the n of r comma omega. Unique element in shift space such that for any I less than this, the ith entry of this is equal to the ith entry of omega. I'm just going to draw this using ticker tapes as well, just so that it is more clear. So I take a sequence, I wait until my condition happens, and then I chop it off, and then I start looping. That's the idea. It's a perfectly legitimate point in shift space. It's a periodic point and all that. Okay. So if you read this proof in Falconer, he doesn't talk about the shift spaces or how it is related to shift dynamics and stuff, but because I'm a dynamicist, I like to use, instead of indices and stuff like that, just dynamically relevant sets. So let's use ticker tapes. I'm going to draw three things. I'm going to have omega sub r, and recall this notion of a cylinder set. So the cylinder set defined by omega sub r, omega cut r, okay? So So omega was an arbitrary arbitrary sequence. It was an arbitrary element in shift space. So I have numbers here, omega 0 or symbols, omega 1, omega 2, omega 3, and somewhere here I have omega sub n comma n of r comma omega, and then the next term omega sub n of r comma omega plus 1, and so on. Keeps going. Omega doesn't know what to do. But omega cut r does the following, you see? Oh, maybe this should be minus 1, actually. Yes. Let me draw these bigger. Keeps going like this. To get omega cut r, I'm going to duplicate all of these entries, but here I'm going to go back to omega 0 so that I have a loop, so that I have a periodic point. See, now I'm not going to use the same number. I'm going to use omega 0. And it keeps going like this. So for instance, here it's going to be omega 1 and so on. Okay? And then the cylinder set defined by this looped version of omega is going to be, well, okay, take the first n of r omega entries, and then the remainder use wildcards. So you have a subset. Okay. Yes.
So is W cut R looping repeatedly or just?
Yes, it is. No, it is. It's a periodic point. Yes. With this period, possibly earlier, but certainly with this period, you keep repeating. In fact, in this case, you're repeating exactly at this time because of the stopping time. Any other questions? Yes.
Remind me just the notation of what we're doing for n, and then in parentheses r sub w here.
This is okay. So I'm saying that based on the fact that this sequence r sub n is a strictly decreasing sequence, there's a unique number. That unique number, I'm thinking of it as a function of r and omega.
Interesting. All right. Sounds good.
Because it depends on r, of course. If r were smaller, I would need to sort of wait longer. Or if omega were sort of like a different sequence, maybe I would need to wait less or something. But once I have these two choices, this stopping time condition gives me a unique number. Okay? So, put P sub r to be all those cut versions. There's a certain subset of the set of periodic points of shift. Okay. Now, for this part of the proof, we're not going to need this, but it is true that this set is in fact finite. In fact, I'm going to give that as an exercise. To come up with sort of like a bad upper bound, it's not that hard. You can just count it, but to get a nice upper bound, it requires some argument. But for now, let me just say exercise for any r between 0 and 1. This collection of periodic points that I obtain by cutting at time r is in fact a finite set. Of course, this is not a finite set, but the looped versions end up being finite. Okay? So, what is next? Okay, here are 3 ideas or observations. So for any omega, omega cut r, 2 is a shift in and of itself. So I can feed it to the cocycle if I want it. And I do want to do that. So, so note, okay. For any I less than n of r comma omega, well, I guess I did write this over here. Let me keep writing it over here, actually. So that's 1. What is out? What's out? Okay. So the n of r omega is also the same as n of r omega cut r. I'm literally using the same symbols after all. If I need to cut omega at n, I need to cut omega cut r at n as well. Because, and for any point in shift space, there's a unique point in P sub r such that omega cut r is eta, which means that you don't sort of like use the same sequence multiple times to get multiple points in P sub r. You only get 1. I'm not saying the other way around. Of course, it might be the case that given any point in P sub r, there might be multiple sort of general sequences that generates this. That might happen, but not the other way around. Okay. And so now what I'm going to do is the following. Recall that I had this U. I'm going to look at the image of U under my cocycle up to these stopping times. Consider the collection. Now U is open. Each of these functions is a composition of finitely many similitudes. In particular, they are homeomorphisms. And under homeomorphisms, images of open sets are open, which means that each of these is an open subset. This is a collection of open subsets. I'm going to leave it as an exercise that, in fact, any two open subsets in this collection is pairwise disjoint. How do I write this? Okay. U1, U2, and curly U sub R. This is pairwise disjoint. Okay. Okay. You have that. And furthermore, I think I'm going to leave this as an exercise also. I have the following. Okay. In other words, the images of the attractor under these specific times covers the whole attractor. Certainly, this side is a subset of this because, after all, the attractor is invariant under the cocycle or any transformation in my iterated function system. But conversely, if I were to take any point in the attractor, well, that corresponds by the Hutchinson coding theorem to some address. There may be multiple, but at least there is one. And so based on that address, there's a unique time where I should be cutting it, which means that it has to be here. Okay? And of course, based on this idea that we had about the closure of U, or its iterates under the Hutchinson operator, this is a subset of this. Okay. I should also mention that in this expression, for instance, I could have put the bar here instead of putting it here. Why? Because this is a closed subset, and this is a homeomorphism. Again, by the similitude assumption. Okay. Any questions? Now we're getting closer to using the covering lemma. So this is going to be one of those covers, you see. So what do I need to do? I need to take a small ball, let's say of radius r, and I'm going to try to see how many of these open subsets, or rather closures of such open subsets, do I get to hit using that ball. Let me start writing it, and then we can take a break. We're almost at the end. Yeah, U is a non-empty and bounded open subset, which means that given R, there are two numbers, lambda and rho, exactly as in the statement of the covering lemma. And there are 2 points, x and y, in X, such that U contains an open ball, or the open ball, centered at X, of radius lambda times r. And in turn, it is contained in the open ball centered at y of radius rho times r. Because each of these guys is a similitude, if I were to apply them to this ball and that ball, the images too would be balls. So, OK, let me not write it. But we're getting there, as you see. Once we have this, because these are similitudes, I can apply this to this side and that side to get an inner ball and outer ball for each element in this cover. So we're sort of essentially right now trying to prove that U sub r, so curly U sub r, is a cover that one can input into the covering lemma. OK, let's take a break, and then when we get back, we're going to continue. OK, I think we're all back. Let's continue. So we were talking about this fact that we're on the way of verifying that this curly U sub r, for any r between 0 and 1, is an open cover, or it's a collection of disjoint open subsets that one can use in the context of the covering lemma. And so because we have that U is non-empty, there's an open ball inside it. And because without loss of generality, U is bounded, it is included in some larger ball. And I can figure out the numbers lambda and rho given R such that this happens. OK? Because my iterated function system is by similitudes, I know that the image of any ball is again going to be a ball. OK? So if you didn't have similitudes, that would be a problem. Because if you had a general contraction, you don't really have that much of a control as to what the geometry of the image of a subset looks like. But in the case of similitudes, you have perfect control. You know that balls are going to go to balls. And in particular, so if I were to apply this particular cocycle, or element in the cocycle, phi of omega comma n, at this nice time, applied to this ball is going to be, well, exactly, I need to track where the center goes, and I need to scale the radius appropriately. The appropriate constant, obviously, is the Lipschitz constant. So this ball is equal to this. So the ball is equal to the image of the ball. But because this smaller ball is inside U, the image of the smaller ball is going to be inside the image of U, which in turn is going to be inside the image of the larger ball. Again, by the fact that this is a similitude, I can take this inside and get this. You see? Having that U contains a ball like this and is contained in a ball like this gives me that this particular image of U, which is an element in curly U sub r, contains a ball like this, and it is contained in a ball like this. Okay? But in the covering lemma, we need the radii to be constant. So they can depend on two numbers, maybe 3 with r, but not more. But here I have many numbers. So I need to do something about this. First, let me sort of abbreviate this stuff so that it is easily readable. Let me call this point x sub omega and this point y sub omega. Omega coming from p sub r. Now, maybe I shouldn't have deleted this. Let me just leave this. And this guy, this Lipschitz constant, is exactly r sub n. And so is this. Okay, so abbreviating everything, I have the following. So x sub omega less than r sub n lambda r is included in this ball, or in this open set. Which in turn is included in y sub omega bar less than r sub n rho r. Now recall the inequalities for r sub n. We had the following. R sub n minus 1 was greater than r, which itself was not less than r sub n, which itself was strictly greater than L sub r. Hang on a minute. Oh, I don't want r's here. OK. Don't want r, don't want r. I don't want r there. Don't want r there. OK, now it works. This, then I don't want this. OK. Because r sub n is bounded from below by this, well, I can change this factor, and that would give me a smaller ball. That is to say, now I have L lambda r, which is a subset of this. It's a ball, smaller radius, which means it has to be in there. And likewise, this, you see, is bounded from above by r, which means that if I were to replace r sub n by r, that ball would increase, quite possibly. So you see, I was able to come up with one ball inside and one ball outside of each of these elements.
Were there white headphones left in here?
Yes.
Oh, perfect. Thank you so much.
Sure. She's going to be famous now. No, I'm going to blur. OK. OK. So that means that we can use, for any r, curly u sub r in the context of the covering lemma. But instead of having L sub, so instead of having only lambda, we're going to have L sub lambda. OK. Still, it works. Any questions about this so far? So you see, for a large part of this class, we were always trying to control the upper bounds. But in this case, we're trying to control the lower bounds. So somehow, even though we want contractions, we want them to not contract too much. You see, that's sort of like a general idea. If things are contracting too much, then in a sense, you again lose control. And whenever there's sort of a non-trivial thing is happening, as far as I'm concerned, maybe, quite possibly, it is related to controlling sort of how much things are contracting. You want to put a lower bound as to how much things are contracting. OK. So let me write it like this. Let me write it in words so that it is clearer. Thus, any element in the collection U sub r contains a ball of radius this, of radius L times lambda times r, and in turn is contained in a ball of radius rho times r. And in turn is contained in a ball of radius rho times r. Okay. Well, the covering lemma says something about such covers or such collections of open subsets. But I need a measure. Well, the measure in this case is going to be nothing but d-dimensional volume. So my alpha is d, because d was the dimension of the Euclidean space, r to the d, which is equal to x. And the covering lemma to be volume, or d-dimensional Hausdorff measure too, if you want it. Alpha is d, and for any z in x and for any r between 0 and 1, if I denote by p sub r comma z the collection of those things, well, let me just say v in curly u sub r such that the ball centered at z of radius r intersects the closure this has at most, what was the bound? 1 plus 2 rho divided by lambda to the power alpha, but lambda in this case is L times lambda. And my alpha is d. So this means that if I were to take any sufficiently small ball, and if I were to look at sufficiently small open subsets generated like this, then I have a nice upper bound as to how many of those images I intersect using this ball, which is this number. Okay. Now here, I didn't mention this, but here L comes from the iterated function system. Rho and lambda comes from the open cover, open set U. If I were to choose a different U, quite possibly lambda and rho would need to change. But you know, all I need is this this upper bound, really. Doesn't matter. And of course, the reason why there's d here is because I chose the d-dimensional volume, which is the obvious one. Because for the d-dimensional volume, you see, the sizes of balls does grow like radius to the d. Any questions about this?
Does it say 1 plus 2 rho?
Yes. Yes, 1 plus 2 rho. We're almost there. Almost there. Recall that I was trying to use nu sub w comma p, this dynamically defined measure, to verify the mass distribution, or to verify that the mass distribution principle has all the assumptions, so I can use it. And so let's look at this then. Before that, maybe I should do something else, but maybe I should write it. i.e., what do I need? I need something like this. There's a gamma positive and epsilon star positive, such that for any subset of X, if the diameter of the subset is bounded from above by epsilon star, then I have some control over the size relative to this probability. After all, I know that this, because it is given by a push forward, it's a probability measure supported. We're going to discuss what that means probably on Tuesday. It's supported on the attractor, which means that the size of the attractor relative to this measure is actually 1. I want it to be positive in general, but I have something stronger. I have that it is 1. Okay. Now I'm going to leave it as an exercise to justify that instead of having this statement, I can just look at the intersections of the attractor with sufficiently small balls. So let me have star here. I have 6 minutes. I hope I'll be able to finish. It suffices to verify orange star for B of the form Z R open ball intersected with this. For any R between 0 and 1, and for any Z and X. It requires some argument, but it's not that complicated. I mean, it is somewhat technical, but it's good. Because typically in measure theory too, this is like a general idea. Typically we have these like general statements for any subset whatsoever. You have to have this, but typically there are shortcuts that you can take. You can also just verify the statement for nice subsets, and that seems to be sufficient. So what that means is that I want to figure out the measure nu sub w comma p of one of these intersections. Let me first look at the following. So let omega be in the preimage of one of these subsets. Okay. Well, by definition, omega cut r is in p sub r. Okay? Now recall one of the properties of the coding map, which is the commutation relation with the cocycle. This equals, so I can take out a factor of the cocycle. But of course, I'm going to use this special stopping time. Okay. Well, this guy, by definition, is a point in the attractor, which means that this point is in the image. Okay? Is in the image, which I believe I left as an exercise, that this, in fact, is included inside. Oh, I think I mentioned this. It's included in the image of the closure of U. Omega, comma, n of r, comma, omega applied to U closure. Which means that this point has image both in this ball and in this closure. That means that by definition, not only is omega cut r inside the collection p sub r, but in fact it is in p sub r comma z. Okay. Or u sub r comma z, whichever. That means that, oh man, 1 minute, please. That means that this is included in the union of the cylinder sets, where this comes from p sub r comma z. We're almost there. Right? There's one more calculation that is not complicated, but it's going to take time to write down. And once we have this, once we verify this calculation, we're going to be done with the proof. Okay, thank you. I'll see you next week.